Thank you, Michael. And thanks to the organizers for inviting me. Of course, it's a great honor to be invited to speak on an occasion like this that's recognizing and celebrating the work of Blaine Lawson, who has had such a tremendous effect on our lives and in geometry and on all the people that have come to know him. I feel like unfortunately I probably used my best story about Blaine on the banquet the other night. The only thing I forgot to say, although I was reminded of it a little later, was I forgot to tell you about the mace and the other effects that happened in the incident in Paris. If you weren't at the party, I'm afraid I can't enlighten you on that right now. One of the ways that Blaine's work definitely influenced mine over the years has been Blaine's work with both alone and with Rees has inspired a lot of questions about constructing examples and understanding systems of PDE that arise from these in these special geometries, and that happens to have been a very happy marriage for me because one of the things I've always been interested in is understanding the kinds of geometric structures that arise, special geometric structures that arise in the various different special geometries, starting of course with the manifolds of special holonomia, but also calibrated submanifolds in special different geometries and so forth, where the system of PDE involved in understanding it turned out to be overdetermined, and the standard methods for understanding what the solutions look like, even locally, were not adequate. So one had to call on the machinery that was developed by Cartan in particular, but also by Chern and several others of Cartan's students and followers over the years. So I thought it would be appropriate today for me to talk about a particular case like this, a system of equations for a structure in geometry that has arisen in a more recent kind of interesting development in geometry, that is generalized geometry, and for which fortunately we have one of the originators of the subject here is Nigel Hitchen here in the audience, and generalized geometry is now roughly about 10 years old, maybe a little older, and the thing that I want to talk about is a special structure that arises in studying generalized geometries, and that has turned out to have connections with Einstein manifolds and Einstein manifolds and extremal Kähler metrics and so forth. And it's, in generalized geometry, the basic thing one starts with the places you should look, Hitchen and Gualtieri, approximately 2003. It's you can think of them in terms of sort of an analog of classical geometry, where you replace the tangent bundle by the tangent bundle plus the cotangent bundle, which has its own natural neutral signature metric on it, and the kinds of objects that one studies, Kähler structures or complex structures and so forth, symplectic structures, can, while they have a nice unified picture, when you look at them in this sort of tangent and cotangent on equal footing, they can be sort of decoded and separated back out into classical geometric objects, but usually it's more than one classical geometric object. It's several things that have to interact in a particular way, and the sort of structure here becomes related structures here in the classical picture. Classical. And the object that I want to talk about, the geometry I want to talk about today, which is ambi, and I'll define everything, ambiKähler. Structures. Can actually be sort of reassembled back over into the generalized geometry picture, but what I want to, but to save some time today, I'm going to start in the classical picture. An ambiKähler structure is the following kind of object. It's actually a pair of Kähler structures. Which I'll think of as a G plus or minus and J plus or minus, where G is a metric on M. And today I'm going to stick with a four-dimensional manifold, a pair of Kähler structures, G plus or minus, J plus or minus, that will satisfy some compatibility conditions. The first compatibility condition is that the conformal structures are the same. So in a sense that we're looking at conformal structures that are actually Kähler with respect to two different metrics in the conformal class. That's one. The complex structure is integrable, and it turns out that one can, for the purposes that we're going to be interested in, one can reduce to the case that that these guys commute. And that leaves, and of course I don't want them to be equal.
You don't even want it to be minus.
Oh, I don't want it to be or minus, right? Not plus or minus, right? Yeah, I don't want the trivial case there, right. This just bracket as endomorphisms. That's right, and there's a choice now since they commute and they're not plus or minus each other. There's a choice about whether or not they induce the same orientation or not. And it's said to be biKähler if they introduce the same orientation, and ambiKähler, that is sort of like ambidextrous, if they induce opposite orientations. J plus and J minus have opposite orientations. And that's what the ambi is for, is that they induce opposite orientations. Right. Now, the question is how many such structures there are like this, up to diffeomorphism, obviously. It seems to be a fairly overdetermined problem, and you might think that there won't be very many examples, non-trivial examples anyway. But in a paper that it's appeared on the arXiv in 2010. There was by Apostolov, Calderbank, and Gauduchon. Calderbank, Gauduchon. and that's math DG 10100992. They investigated the toric case, studied the toric case. And they showed that it had a surprising, there was a surprising number of solutions, surprisingly large number of solutions, even when you impose this. And by toric here, I mean that there's a two-parameter symmetry group that's Lagrangian with respect to both Kähler structures. That was their assumption. And it turned out that there were a lot of solutions, and they were actually very closely tied to Einstein manifolds. There's a natural way to associate construction in conformally Einstein metrics, and that they were able to exploit, and were able to come up with examples of not only Einstein Kähler structures like this, but also extremal Kähler metrics and a number of interesting geometric examples that they found in their classification. But they left sort of unsettled how many such structures there are. This is, if you, which is a natural thing to ask for, especially if you don't know that there's you don't know how many there are. Sort of the first thing I think of when I look at something like this is to sit down and say, well, what does the general solution look like, even locally? And it turns out that there is a nice answer to this, but it's surprisingly delicate, and that's what I wanted to talk about today. If I have time at the end, maybe I'll say something about what their results were in their constructions of, for example, the extremal Kähler metrics and the self-dual Hermitian Einstein metrics that they found by this method. The fundamental object that you can look at that sort of starts off understanding what these things look like. There are two things to bear in mind. First of all, there is if you just from this, it's easy to see that if you define Q to be J plus times J minus, because they commute, Q squared is the identity, and Q itself is not the identity, not plus or minus the identity. And from that, it follows without much trouble that in fact the tangent bundle splits into a plus eigenspace and a minus eigenspace, two distributions on the manifold. And it turns out that the geometry of these structures really depends heavily on the nature of these two-plane fields. This is a rank 2. And in fact, what I'll do is I'll take the thing that's interesting, because there are two plane fields in dimension 4. The only real invariant of the two-plane field is how large its bracket is. That is, for example, it could be integrable. That is, the bracket of the thing with itself could be two-dimensional. The bracket could be three-dimensional, and then the iterated bracket could be the 3 or 4, if that's 3. And in fact, I'll let R plus or minus be the rank of the second bracket. And that's R plus or minus is in 2, 3, or 4. And it's not necessarily constant, but on a dense open set, you can decompose it into dense open sets, for example, for which it will be constant. And that will turn out to be useful simply because it turns out that you can understand very well what they look like in these big open sets, and then from that you can hope to figure out how to cross the walls, so to speak. And there's now that I've got this here, let me actually maybe I'll put this here because I'll need a fairly large space for this.
Does that mean the number of linearly independent vectors in the plane?
That's right. Yeah. Look at the span of all the brackets of things in, say, D+. That's either 2 or 3 dimensional, and if it's 3, then this could be 4, right? Of course, if it's 2, then it stays 2 forever, right? What I want to do, and hopefully I always stand too close to these things. Not too bad, maybe. I want to sort of make a grid of, so this is going to be R minus and R plus. Obviously, switching J plus and J minus, I can switch the two things around. That's not going to affect those things. So this picture is actually kind of symmetric, is naturally symmetric in a way. And if you look at the examples that they write down, they get examples in here, in here, and in here. They don't get examples over here. And it turns out that breaking the problem up into these, 9, but really only 6 different possibilities is what gives you a handle on what's going on. One thing you can see right away, so sort of the easy case is, and we can pretty much dismiss it, is when R plus or minus is 2. That is down at the bottom here. Because in that case, say the two plane fields being integrable, actually it turns out forces the metric to be a product. So this is the product case. That is, it turns out that locally anyway, M is a product of M1 cross M2, where M1, let me call them, M1, where Mi is a Riemann surface. And J plus is just J1 plus J2, and J minus is J1 plus minus J2, and actually this is Riemannian surface. Right, sorry. Riemannian surface, and there's actually a G is actually G1 cross G2. Everything uncouples in this case.
So the conformal factor is actually 1 in this.
The conformal factor is 1 in this case, it turns out. Well, it's constant. There's a little bit of slop in this, in that you can multiply either G plus or G minus by constants, and that little I'm going to ignore that, but it's actually I'm going to basically ignore that because that's a kind of trivial modification.
So these are just foliations then?
That's right. So the manifold is foliated, but the metrics actually push down on the leaves. It's a Riemannian foliation, in other words, in both directions. But still, that gives you of course, generically a metric, MIGI, an oriented surface like this, that still locally, of course, a metric depends on one function of 2 variables, modulo diffeomorphism. So there's 2 of them, so I'll call this like 2 of 2. 2 functions of 2 variables is how many functions, but this is kind of the trivial case. It's not the, it's not.
Exactly the foliation that gave the discrete subgroups that L2R,
Right. Yes, right, actually metrics, right, yeah. So they're global dynamic problems, actually, yes. Yeah. And the toric case turns out to be the case that, which is, their examples specialize in this case just to be the case where each of these is a surface of rotation. So that's not, so that one's a little bit harder, is the case next. Oh, maybe I better leave it over. Yeah. A little bit more interesting is case 2 is when, say, R plus R minus is 2, 3, or 3, 2. And those actually, there is a, it takes a little work to figure it out, but you can. It's, and what you find out is that, local, there exists local coordinates, x, y, p, q, and they're not quite unique, but they're close to it, so that the metric looks like, there's one thing that I haven't said here. Oh, I can put it right here. This is good. Come down here. The fact that they induce they have opposite orientations means that when you square omega plus, it's going to be a negative multiple of omega minus squared. And I just have to figure out what the multiples are here, but the way I'll do it is I'll just write this as e to the s and e to the minus s, where s is a function on m. That is, oh, there's a minus here, sorry. Because this guy is because they're opposite orientations, this is their negative ratio. And this s is now determined. If I'd scaled by constants, I would have added a constant to s. But
are they plus and minus with Kähler forms?
Yes. Oh, sorry, I didn't say that, did I? Yeah. Yeah, they're Kähler structures with Kähler form omega plus minus. 2 forms. And square is wedge square. That's right. Yeah. Sorry. Thank you. Yeah. And this sort of common scale factor that brings them to a single a common area form. What that means is that there's a metric which they call the Apostolov, Calderbank, and Gauduchon call the Barycentric metric. That there's this sort of central metric that's a minus there. Right. That's their common multiple, and the reason I needed to say that is because if you make that definition, then in this 2-3 case, it turns out that the solutions G naught turns out to be expressible the following way: s prime of x dx squared plus dy plus a pq dq squared plus a pq dp squared plus dq squared. And this s is that s, where what we require is, of course, that s prime is positive and the partial of a with respect to p is positive. But otherwise, a and s are arbitrary. These coordinates are essentially unique. There's one thing that's immediate from this formula is that the metric is that you can translate in y because y only appears as dy. So there's always a one-parameter symmetry group for these metrics locally. Typically, there won't be any more. It's not too hard to actually do this. I mean, you use the integrable coordinates that you get out of the dp and dq, which are d plus is d plus is d by dx. D plus is the kernel, is dp equals dq equals 0, and d minus is the other guy. Dx equals dy plus a pq dq equals 0. I'm not going to, don't worry, I'm not going to write up the normal forms for all of them because that actually would take quite a while. But I wanted you to see roughly what an example looks like. But the general solution, this is the general solution up to diffeomorphism, and the solution depends on one function of one variable and one function of two variables. So one of one, one of two, and one symmetry. And similarly over here. Okay. And the calculation needed to prove this is, like I said, it's not something that anybody would have too much trouble with if you sat down and just, wrote out what it meant for things to be integrable and so forth. So that's the next simple case. One more case that actually turns out to be easy, but it turns out to be easy for a kind of a subtle reason, is r plus r minus is 2, 4, or 4, 2. That turns out this can't happen. I don't know a really simple proof of this, but it can't. And I wanted to eliminate these because all the cases where one of r plus or r minus is 2, because those are their treatment is going to be considerably different from what's left in the other cases. One thing that you'll notice right, maybe I can't say that yet. Yeah, this is not too predictive of what you might figure out in the higher things, but the thing that I wanted to say is what you would expect is what you might have expected is that as you impose fewer and fewer conditions, the generic thing for a pair of distributions, would be that the ranks of these two would be 4, and so you would sort of expect that that as you weaken your conditions, that is by allowing the r's to increase, that you might get more solutions. And this is that's why this is a little bit surprising, this empty set here, because it looks like you've weakened the conditions, but then it turns out that that's incompatible. So, okay, so let's set this aside from now on. Let's assume that the r plus and r minus are all bigger than 2 from now on. Then what you get is there's a little sort of normal form that you can write down. It's a not very hard proposition that says that there is G0 orthonormal coframing, omega, which is omega 1, omega 2, omega 3, omega 4, such that omega plus is e to the minus s omega 1 wedge omega 3 plus omega 2 wedge omega 4. Omega minus is e to the s omega 1 wedge omega 3 minus omega 2 wedge omega 4. And omega 1 is the bracket of d minus defines this, while omega 2 defines the bracket of d plus is, these are rank 3 distributions. These are rank 3 distributions, and they're defined by the vanishing of a form. So having this be rank 3 is enough to sort of single out a particular coframing here. Up to there's obviously some signs that you can flip the signs in omega 1 and omega 3, omega 2 and omega 4, and so forth. But this is almost unique. It's almost uniquely defined. And what are the conditions? If you look at what is the integrability conditions, of course you have d omega plus and minus or 0, and the complex structure comes from, so J plus is the 1,0 forms of J plus are omega 1 plus I omega 3, omega 2 plus I omega 4, and omega 1,0 J minus is omega 1 plus I omega 3, omega 2 minus I omega 4. Those are so the conditions that this coframing and the function S has to satisfy are exactly that, and this is necessary and sufficient, that these forms have to be closed and these two systems have to be differentially closed. That is, they have to satisfy the Nine-House tensor. The d omega 1,0 J plus or minus is contained in the ideal generated by 1,0 J plus or minus. So that's the full extent of the differential equations. If you this is of course 3 differential equations, so 4 differential equations on the vanishing of these 3 forms. The vanishing of the Nine-House tensor is 2 differential equations in each case. So it's a total of basically 7 differential equations that have to be satisfied by this data, this coframing and this function S. And it's at this point that the method of Cartan for understanding the solutions of these differential equations really comes into play. And before I do the try to describe what the method is, let me go ahead and relieve any suspense you might have by telling you what the answer is in these cases. In the case where it's 3 and 3, it turns out that it's 2 functions of 1 variable. That is, there are 2 arbitrary functions of 1 variable in the general solution, and there's always a 2-parameter symmetry group. In fact, these examples are all toric. They're in their sense. And this makes up the bulk of the examples that A, C, G, toric. Makes up the bulk of the examples that they construct here. It turns out to be this case where both forms have rank 3. Mm-hmm. Well, it turns out that, yeah, so what's the difference between local and global here? As long as the rank is constant here, there's a local normal form, and there's actually a submersion onto the leaves of these rank 3 distributions. So what happens is you have this 4 manifold that maps onto 2 lines basically locally, and the arbitrary functions get specified on those 2 lines. And there's an explicit formula that says you give me an arbitrary function on this line, an arbitrary function on this line. There is a metric in this class. There's a ambiKähler toric structure on this on a 4 manifold that submerses onto those 2 lines, generating those 2 functions. That's the and if the lines have metrics on them, and if the function is if the line is complete, then in fact the constructed thing is complete too. So you actually get complete solutions that way. In fact, they go through and analyze which of these things in this family give you Einstein metrics and which give you extremal Kähler metrics and so forth. And there's a relationship between what they call the polystable condition for constructing certain solutions here that they relate to things in algebraic geometry, but that's maybe something
Are these complete on a closed manifold, or are they complete on open sets?
They're complete on the in this case where in the 3-3 case, if the functions are defined on 2 complete lines, then the manifold that's constructed is actually topologically its simply connected cover is R4, and it's complete on that R4. The metric is complete on that R4. So the topology of these things is not so complicated, but then it turns out that the method they use to construct the associated Einstein metrics, when it's associated to an Einstein metric, actually produces something that's you actually have to scale and collapse in certain directions, and you get orbifolds. So they use this to actually construct Einstein orbifolds in dimension 4. I refer you to their paper for the examples. Right? So, and it was actually at this point that I entered the picture. I talked with David Calderbank, who said that they'd been able to handle the toric case, but they couldn't figure out what to do in the general case where they didn't assume any symmetries, and so I thought about it for a while and realized that once you got it to this stage, as I said, you can sort of, and as I'll explain in the remainder of the talk, you can actually turn it into, you can actually analyze it from the point of view of exterior differential systems in a very nice way. But they didn't know, other than these toric examples that they knew sitting up here, they didn't know that there were any other solutions. And the toric examples that sat up here they had only a 2-parameter family of them. Well, so what happens in these 2 cases, and I'll tell you, and then I'll try to explain why it happens. It turns out that these guys depend on one function of one variable, and there's so the 4 manifold submerses onto a line. That line, you get to specify an arbitrary function on that line, and if that function is complete on that line, you get a complete metric. And there's generically no symmetries. Generically. In fact, you can never have more than one parameter symmetry, which is why they couldn't see these. And less than or equal to 1 always. On the other hand, this one, as I'll explain, when I get into the proof, this one turned out to be the most complicated. In some sense, you would think that it's the most general because you put the least restrictions on the low order invariance, which is what the brackets are. But it turns out that these they're very rare. There's a 6-parameter family of these, constant 6-parameter family. And generically, there's a 1-parameter symmetry group. So, in fact, as you sort of weaken the conditions, it, in a certain sense, except for these places where there's no solutions, it actually gets more rigid as you weaken the conditions, which was not something that we expected. So I want to explain how this gets filled in, and in the time remaining, and because it's actually it's not a routine calculation by any means, and it actually turns out to be very interesting from the point of view of PDE. So how do you get started on this? Well, these equations, of course, tell you something about the derivatives of S and the omegas, and what they don't do is they don't tell you all of the derivatives of the S's and the omegas. They tell you part of them, but they don't tell you everything. And so what you get, and I'll write up this so that you'll see what it looks like. And this is just uncoding, just decoding these integrability conditions. The lemma is that there exist U1, U2, not 0, A0 through A5, functions on such that first, ds is 2u1 omega 1 plus 2u2 omega 2, and I'll ask for your patience here for just a minute. D omega 1 is a2 omega 2 plus a3 omega 3 minus a0 u2 omega 4 wedge omega 3 d omega 2, and I have a purpose for this, but don't worry, I'm not going to fill the rest of the lecture with formulas. Omega 1. Whoops, that's a1 omega 1. A4 omega 4 and a0 u1 3. The formulas aren't exactly important, but you need to see one thing about them. That's a minus. And finally, we need the formulas for du1 and du2, which are pretty easy.
the minus part on the.
There's a minus here and a minus here.
Could you check which ones are E's and which ones are U's? They kind of blur.
Sorry, that's a U. That's a U. Those are U's. And that's a U, sorry. And anytime there's a product, it's an A and a U. Right. Now, why did I write this up? The point I want to make is that what is this? It turns out that the only way S ever shows up is in that equation. It doesn't show up anywhere else. And it can essentially be discarded because the only thing it's really saying is that this this one form is closed, and that's a consequence of these equations. So you can basically throw the S away. It's really these equations that matter. And the structure of these equations is the following. And they're saying that you have formulas like this that say that d omega is some expression, which I'll call L, which depends on U, some linear function of A applied to omega, wedge omega, and du is another function of U, A omega, where what you should think of is, of course, omega, wedge omega is taking values in wedge 2 of R4, and the A's are appearing linearly in the formulas. The U's, we have formulas for the 1 forms and the 0 forms, and their derivatives in terms of 6 unknowns, where L and LU and KU are maps of R6 into HOM, so plus here like this, into HOM lambda 2 R4 plus HOM R4 to R2. That's what the structure of the equations is. And what it's saying is that you have unknown forms and functions whose derivatives are expressed in terms of those forms and functions, plus some unknown, plus some free derivatives, so to speak. Think of A's as A's are free derivatives. And K and L are some, well, you can read off what they are from here. They are, well, L and K are some linear expressions with coefficients that depend on U's that tell you how to express each d of omega I as some coefficients times wedge products of omegas. That's all it's saying. That's the structure of the equation. And similarly, the derivatives of the U's are some linear expression, well, affine expression in A's and with coefficients in U that tell you how to express the omegas in terms of the U's, the D's. Now, this is precisely the mechanism that you need to apply the machinery of the Spencer theory for overdetermined equations, which is actually an elaboration of Cartan's theory of overdetermined systems, and that was then, developed further taken up again in the 50s and 60s, and so now once you get it into this form, you can apply the Spencer machinery. And here's what the Spencer machinery tells you. So call this system, this combined system, I'll call it 1. Well, if you just take the exterior derivatives of these equations, they'll give you formulas, they'll give you restrictions on dA and on dA. You know the derivative of everything else, you just don't know the derivatives of A. And so when you differentiate these equations, what you'll find is that you get an expression like this, where B is B1 up to B6. And so J is a map of R6 into HOM R4 to R6. So you know the derivatives of the A's, except that there are there are 6 free derivatives in the formulas for the dAs that just follows from taking d of these equations. So you need the derivatives of the b's. You take the derivatives of the b's, and you get I think I used the letter G, U, A, B, C, omega, where C is C1, C2, C3. And you take the derivatives of these and you get formulas for DC. Don't worry, I'm not going to keep doing this. E. And E is E1, E2. Okay, right, I had to skip D, obviously. Right. Okay. Right, so at this point, so this F is a map of R2, and here I'm running out of space, but F is a map, F of U, A, B, C is a map of R2 into HOM R4, R3, and at this point, the Spencer machinery tells you that you can stop differentiating because this is involutive. The symbol is involutive. The symbol's involutive, and if the system were actually in involution at this point, it would say that the solutions depend on 2 functions of 1 variable. That's what you would get if you were here. But, and here, let's see, I'm gonna have to erase that. And I can erase this. But again, the Spencer machinery tells you that the characteristics of this involutive tableau turn out to be omega 1 and omega 2. And moreover, the characteristic variety of F is omega 1 and omega 2. Notice I didn't say the system was involutive. I just said that the symbol was involutive. To actually get the system to be involutive, you have to check one more derivative. But the very fact that the characteristics are now omega 1 and omega 2 tells you something. And that's why the brackets of the D's make a difference. Because remember, omega 1 equals 0 defines this guy, and omega 2 equals 0 defines this guy. And there's a theorem of Ofer-Gauber that says that for an involutive system, the characteristic variety is involutive. If the system is involutive. And you can read off whether or not this is involutive. That is omega 1 an integrable form? Well, it's not an integrable form unless it can't be integrable. That is, omega 1 wedge d omega 1 equals 0 if and only if A0 and A2 are 0. And d omega 2 wedge omega 2 is 0 if and only if A0 equals A1 equals 0. So unless both of these things hold, it cannot go into involution at this point. And in fact, because the characteristic variety won't be involutive, both of the characters will have to go away. And that's why if you don't have those two if you don't have those equations, the solutions can only depend on constants because the characteristics have to go away. And that's why you cannot get arbitrary functions here. You can't get, if these aren't integrable, you cannot get arbitrary functions here. And in fact, exactly what happens is, if you now set all of these equal to 0, if you set these equal to 0 and calculate, you get, now you have a much simpler system to work out, and you get these guys, exactly these. If you set one of those characteristics to be involutive, depending on which one, whether it's a D plus or D minus, you get this one or this one. And one of the characteristics survives and the other does not, exactly as predicted by Ofer-Gabber's theorem. The hard case is when none of these are 0, because now all you know is that the characteristics have to go away in the next prolongation. They have to go away, but what happens? And that's where, let's see. Yeah, I don't want to erase that. So what I can do is, and I'm almost done. So if you now differentiate these equations and assume that these don't hold, what you get is something pretty amazing. I'll just erase this part here. If, say, A0, A1 is not 0, 0, and A0, A2 is not 0, 0, then differentiating these equations gives you number 5, which is just a polynomial. A polynomial, U, A, B, C, E equals 0. This is a polynomial in 19 variables. This is 19 variables. It's not one polynomial, it's 28 polynomials. And they're of degrees 5 and 6. Which kind of explains why they were hard to find. And, well, the obvious thing would be to say, you've got 28 equations in 19 variables, there's got to be no solutions, or essentially no solutions. And if you, for example, if you give it to Maple and say, find the solutions of these equations, every machine that you put it on will eventually run out of memory. The solve routines just don't work. It's pretty hopeless. However, if you order the variables correctly and look for a Grosvenor basis, which turns out to be the right thing to do, it turns out that what you want to do is eliminate C and E if you can, eliminate B, C, and E if you can, but you have to put them in the right order. Then it turns out that the ideal generated by the P's actually turns out to be only 6 equations. So that is, these 28 polynomials actually turn out to lie in an ideal generated with 6 generators. And the 6 generators are not so easy to find. So, in fact, I have no idea how you'd find it by hand. Grosvenor implies ideal generated by 6. Yes, right. But now, if you now look at the variety cut out by these equations, if you now restrict all these equations to this variety, then the system's involutive. It's actually involutive in that case, and the result is this now becomes the structural equations of a Lie algebroid for the unknown one forms. I mean, for the unknown one forms and functions and so forth. And the Lie algebroid turns out, after you grind through, you find out that this variety is foliated by codimension 6 leaves. Those codimension 6 leaves are actually the 6-parameter family of solutions. Now, actually being able to write down, actually being able to integrate these equations, I have no idea how you would do it at the moment. These, you really, if you look at any one of these generators, they're large on the screen. But it turns out, nevertheless, that turns out you get a system that you can actually understand, and I mean that is involutive, and we know now how many solutions there are. Now, what you can't tell is how complete they are. 6 parameters, 6 constants. Yeah, the solutions correspond to the leaves of a. I mean, this guy is foliated in codimension. This variety is foliated in codimension 6, and each leaf corresponds to a solution. That's the local solutions, but in fact, every solution, as long as the rank here is constant, the solution is each manifold is mapped, submersed onto one of those leaves with one-dimensional fibers, and the fibers are
What's mapped on the leaves?
each manifold. So the 4 manifold is mapped onto a leaf. Maybe I didn't count right here. This guy has to be 9-dimensional. So 9, 19. So it should be 10. Right, because I left out those guys. Right. I was counting the B's. I wasn't counting the C's and the E's. Right. So it's 10. Right. Right. So each leaf is 3-dimensional or less. There are some of the leaves, some of the image leaves can be 2-dimensional or even 1-dimensional. But the generic leaf is 3-dimensional, and it's the image under this mapping of the A's and B's and C's and D's of the 4-manifold. And so you get this picture. This is the classic picture of the Lie algebroid. A system of where you can encode the set of solutions of a set of differential equations in terms of the leaves of a Lie algebroid, and which actually it was in Cartan, but not by those names. The theory of Lie algebroids was developed much later as sort of a way to formalize what Cartan was doing, and this is a case where the full all the bells and whistles have to be kind of pulled out to actually solve the problem. I don't think you could. I can't imagine doing this by hand. And it was a little bit of a surprise to me that you actually get to a point where Gauber's theorem plays a role. Because in the past I've never actually seen it play a role before. So you always it was there for reassurance. It wasn't for use, so to speak. But here's a case where you actually constructively use it, and you need it. So anyway, I'm sorry I ran over, so I better stop now. So.
Further questions? So in the work of Apostolov and Collaborations, Bach flat. So in that
That's
case,
right.
You
Yeah.
don't get these extra cases?
Yeah, you don't get these extra cases in the Bach flat case. That's right. Yeah.
So it stops.
Right.
How explicit are the 4-3 case?
The 4-3 case, I have a normal form for that, but along these lines, you write down an arbitrary function and then some. But the expression, if I tried to write up that normal form, it'd take a whole board. I haven't found a nicer way to write it down, but it's very explicit. You can integrate it completely. That's why this case is so annoying that there doesn't seem to be any nice way to integrate it. I mean, nothing is integrable. No combination of anything seems to be integrable. So.
Could be some kind of so the general case you have, for instance, the 6. I mean, this one is the top corner, but then on some submanifold it could be smaller or something like that.
On some submanifold, the six-dimensional variety actually contains, sitting in this variety, there are subvarieties on which A0, A1, and A2 vanish, say. And those cases, for example, will actually, so there are some leaves, some smaller leaves that actually drop down here. But the generic leaf is up there. Yeah.
On the same manifold, you cannot have a mixed.
Well, that's a good question. On the certainly on these guys, these are all real analytic. They're that's another consequence of the structure equations. You'll get that they're actually real analytic. So the only way they could be part of something on an open set would be if somehow or another you could run to the edge of a leaf and somehow or another keep the metric from degenerating even as you run to the edge of a leaf, and then try and continue it non-analytically. I'm not aware that that can happen. In this case, for example, in this case, it can't happen. There's they can't be part of a bigger thing, in fact. But the sixth case, I don't know. I mean, we don't have any explicit formula for them, and it's a very mysterious thing.
Well, you can't be part of a bigger thing. You can always take anything and make it part of anything else.
Let's see. What's the right thing to say? Well, no, you can't. I mean, if the thing is complete, you can't. Right? Yeah.
A little piece of it.
A little piece of it you conceivably could, but the point is, in this case, the only flexibility you have in the open set where you have rank 3, 4, the only flexibility you have is that one arbitrary function, and you can't. If you look at the explicit formula for the arbitrary function, you'll see that the only thing that can really happen is for the function to stop being differentiable or stop existing. At some point, you can't. Its values don't affect the ranks of the two distributions, and so you could have it blow up and the thing not be complete or something like that, but you couldn't smoothly continue it.
So when you're talking about completeness with respect to G0.
Yes, for example, that's right. Yeah, completeness with respect to G0, but there could be completeness. That's right. There could be completeness, because S is not constant. I erased it, but S is only constant when U1 and U2 are 0, which is exactly, of course, the case when the distributions are integrable. And so it can happen that like omega plus, G plus could be complete and G0 not be. I don't have an example like that, but I think you could probably construct examples in this case where that happened.
Does the conformal factor have some special, is it expressible in terms of scalar curvature or something like in the?
There's no identity. You can actually write down the curvature of all three metrics, G0, G plus, and G minus, as polynomials in the U, A, B, C, E. And the point is that because S is not determined by U, A, B, C, E, S is only determined up to a constant, an additive constant. It can't appear as a formula in the curvatures. S by itself can't be. But it could be that the scalar curvature divided by S might be constant or something like that. I don't know. I haven't tried to do those calculations.
Other questions? So, first of all, you very quickly dismissed the two four-case saying, I don't know a short proof.
I don't know a short proof. You have to differentiate a few times to see it, but eventually you reach a contradiction.
You end up with an empty system.
That's right. Yeah, you reach an incompatible system pretty quickly because you set certain things equal to 0, so the structure equations are simple, and then you get to an incompatible system pretty quickly.
So on that point, so for all these other boxes other than the top one, right? The characteristic variety is low degree and low dimension, so it's always based on this, right?
That's right. Yeah. In order to get rid of the functions of two variables, you need that the system not be integrable. If the reason this exists is because the characteristic variety, the U's are 0, and the characteristic variety consists of the omega 1,3 plane and the omega 2,4 plane, and that's why it's 2 of 2 there. But as soon as you lose integrability there, that goes away. So.
If they want to look up off the jabber, maybe we should decide whether it's 1B or 2Bs.
Oh, yeah, right. Is it 2Bs? I think it is. You're right. I think it is. Sorry, I should have. I apologize to offer. Right. Yeah. In case he watches this. Yeah. Yeah.
Yeah. Maybe it's a comment. Is it really so surprising that things get simpler as you go up? I mean, it seems to me that as you lose integrability, then there's more coupling. You've got this kind of
Right.
coupling between
Right.
the two systems.
Yeah.
You get
It's not so surprising that the characteristics become what should be the characteristics become less integrable. So that means that there is going to be some incompatibility that you're going to have to take into account. That's true, but it's a misnomer. I think it's a mischaracterization to say that it gets simpler, because in fact when you get up to the top, it's very complicated, right? Right.
Well, yeah, it's complicated.
It's more rigid. It's definitely more rigid. That's right. Yeah, it's more rigid but the only reason I raise that is something that you might think is as surprising or unexpected is this, that normally what you think of when you think of a system of PDE is that the more equations you put on, the fewer solutions there are, right? And here, if you put on the extra equations that the brackets are zero, then there's more solutions. But it's a case. But this is, you're right. One shouldn't be surprised in the overdetermined case, because it's like the Wild West. Pretty much anything can happen if you're if you ask, can a system have this property? The answer is almost always yes. Right. And so this is a case, in fact, where the increasing non-integrability of the characteristics, what should be the characteristics, is in fact what causes the rigidity to go up, right? So in that sense, it's expected, but you couldn't know what the characteristics were going to be until you did the analysis. So, right. Or I couldn't know. So.
Well, perhaps we should break at this point.
Yeah.
Have a brief.
Right. Okay. Yeah. Thanks. Yeah.